Morning, everybody. So thanks, afternoon already. Thanks, Prof, for the introduction. So I'm going to speak to you guys about CESIMAS. It is a bit of a mouthful, but as we go through, we're going to decompose this name and why it's so complex. So as Prof Ehlers mentioned, it's CESIMAS. It's a continual, evaluative, self-aware, immune-inspired, multi-agent system that gets applied to a CIP environment, effectively the protection of an organization. So a little bit of an abstract. Organizations are reliant on the electronic assets. And I want you guys to think about this reliance purely at a national and an organization level. So within your company and nationally. There's reliance on electronic assets in the form of computers, servers, network infrastructure, and the internet to drive both business operations directly. They might be manufacturing something, or indirectly, for example, access to emails so you can communicate. So there's been a paradigm shift that has seen these different companies, organizations, nationally and also locally, adopt a cloud and metaphysical model. So things like cloud computing is now a common term and commonly utilized within organizations. So these modern organizations rely on conventional security mechanisms to form the concept of their CIP. So I think one of the key things here we need to mention is conventional CIP mechanisms are fallible. So what is conventional? A firewall, a proxy, an antivirus software, and so forth. And what I mean by fallible, there's specific elements there that might cause a let's take, for example, a hack we're going to speak about a little later, where a hack might occur and a data breach might occur. So every organization needs to perform a RVA, a risk value assessment. Should we implement or spend money to protect this specific resource, or do we mitigate the protection of the resource to a third party? One key thing is obviously there, we need an improved CIP experience whilst trying to reduce the financial or resource implications of that. So what is considered critical infrastructure? Well, as we mentioned, it's electronic assets, firstly. It can be physical and intangible. And the protection thereof, the CIP mechanism, is the mechanisms, policies, and procedures that you've implemented to protect these electronic assets. Okay, the main purpose is to ensure CIA, confidentiality and integrity and availability of your data. So a couple of key characteristics of a critical infrastructure environment. The first thing is reliance. We briefly touched on the point that an organization is reliant on the electronic infrastructure. Threats all around us, whether it be external or internal, a hacktivist and a disgruntled employee, and also consider polymorphic threats. So you've got polymorphic malware, consider BYOD environments, so bring your own technology, BYOD, bring your own device environments and BYOT environments. So effort. CIP within an organization takes effort. It takes resources, both financial and human. Is it worth doing a risk value assessment? Should we protect against hacktivism? Should we protect against polymorphic malware? It's kind of going to be an organizational decision. Then lastly, what are the consequences? Well, the consequences are far-reaching. Financial, reputational, brand-driven, and so forth. And we'll touch on a couple of that. So a couple of examples. What this graph illustrates is the amount of data records that have been exposed as a result of a exploitation. Off the top of my head, this is also leading up until maybe the start of 2017. There's been a couple of high-end cases. The biggest one was Equifax, exposed 143 million records. Some of the newest and latest ones, I don't know if you guys are familiar with NiceHash, a big popular, I think it's a Slovenian-based crypto mining platform. A little bit towards the end of last year, they also had a big hack, 4,600 bitcoins exposed. Those bitcoins all got stolen, the equivalent of about 500 million rand. It's probably about like a couple of hundred million pounds, euros, I guess. So some interesting stats around that. There's on average about 555 million victims of cybercrime. Cybercrime being loosely defined as anything that's a crime rated in an electronic sense. We've got an example of cyber attacks. Ironically, most of the attacks happen either from Russia or from China. Not necessarily saying that they are Russian or Chinese, just access to resources and VPNs. So the CESIMAS model is a bit of a complex model and it covers quite a few different research domains. We're going to dive into one of those. So firstly, what are the problem statements? Well, there's no all-encompassing solution to ensure effective and efficient critical information infrastructure protection, CIP, within an organization or one step a little bit higher at a national level. So what are the objectives? Well, we need to address this main issue, CIP issue. How do we implement a holistic CIP solution that's going to augment and complement the current CIP solutions, whether they're conventional or non-conventional? And then how do we make sure that this obviously complements a little bit more efficient and more effective? Some of the research areas that I've conducted my research in is multi-agent systems, artificial immune systems, contextualization of complex environments, and then self-awareness and ambient intelligence. And we'll dive into each one of those briefly just now. So we've heard a lot of talk about multi-agent systems. What is an agent? An agent can be any virtual element that's got the ability to perceive an environment, do some decision making, and execute an action through an actuator. More often than not, a typical agent will be installed with what's called the BDI model. There's a certain belief, there's a desire, and there's an intent. And then, so obviously, what are the benefits of multi-agent systems? Being, how do we have multiple different agents that does similar complementary things in a big environment? Well, we've got knowledge sharing, communication, collaborative problem solving, and so forth. So, artificial immune systems, in a nutshell, is a research field of drawing analogies between the human immune system and a computerized application. Okay. So, the human immune system utilizes the concept of the self whenever cells are generated in your body. In a very high nutshell, very loose description would be that in your immune system, you've got a generic cell. That cell is produced by your immune system and by your spleen. That travels to a specific organ where it takes on a specific form or functionality within your immune system. And so we apply that same concept in the CESIMAS model. This notion of the self describes what should be part of the immune system and what should not be part of the immune system. So a bit of a discrimination process. And then obviously the cells are trained on this notion of the self. So within the immune system, there's 3 layers of protection. You've got things like your anatomic barrier, that's things like your skin and your nose hair. You've got innate immunity, that's the immunity that you're born with, you inherit from your parents and your grandparents. And you've got adaptive immunity, it's just the ability of the immune system to react to flus and colds and that kind of virus things. So the key concept here is, we're going to talk about affinity between cells. So a cell binds to another cell through an affinity, is like how similar are they? And then that binding function and proliferation is going to become quite important. So we briefly touched on contextualization of the environment. We've heard a lot about will multi-agent systems be effective? What is the context of the environment? There needs to be, I get some inputs, whether the inputs can be trusted or not. And then based on the inputs, I need to make a decision, whether the decision is good for me or bad for the environment, a bit of a deliberation process. So self-awareness refers to the ability to instill a basic understanding of an operational environment, whatever that operational environment might be, within this electronic agent, this electronic entity that can make decisions or actually execute actions. So the importance of deliberation decision making. I mean, we briefly touch on what we call reasoning. So for any multi-agent system to be effective, and we use that term effective loosely, depends on your interpretation, there needs to be a couple of key things all pertaining around reasoning. So the 3 core problems is, the agent needs the ability to solve problems, there needs to be some comprehension, some understanding of this environment, and then thirdly, can this agent learn from this environment? And where those 3 things intersect, is this very small little dot. So what are the complexities of a critical infrastructure environment and ensuring protection thereof? Well, firstly, critical infrastructure is complex. An organization has computers on a desk, there might be a server in another room, there might be another network in another country. Span multiple environments, there's geographical restrictions, the company might be a multinational organization, and then these dynamic environments. For example, we've got a Wi-Fi hotspot on campus, everyone can connect to it and disconnect at a moment's notice. So there's 4 key dimensions of ensuring protection. We're going to go through each one of those now. Most importantly, I think conventional CIP mechanisms cover 2. They cover firstly the proactive dimension, so actively monitoring for potential threats. They cover the preventative dimension, once I've detected a virus on my machine, do X, Y, and Z. And so what this model, the CESIMAS model tries and does, it goes beyond that. It goes, well, we want to be reactive. So actively responding to threats as and when they occur, both in a dynamic and a non-dynamic manner. And then lastly, responsive. So emphasize effective and efficient response to get rid of this potential exploitation. Okay. So the CESIMAS model. Firstly, we're going to talk about the positioning. So we've established that it's a metaphysical model. Effectively, it's virtualized by nature. The purpose of this model is not to say, don't use antivirus software, don't use firewall software. It's better to say, how can we complement the current CIP mechanism in the organization without requiring additional investment of resources, and to repurpose the resources that might be available within the organization from a computational point of view. So the positioning is at a virtual layer, and I just position it, let's say we've got some external networks, we've got the internet, we've got a firewall, a DMZ, whatever the case might be. The positioning of the model will be across the infrastructure of the organization, where we might have different geolocations, there might be different subnetworks, and so forth. We've grouped the functionality of the model into 5 key functional areas. driven around specific high-level user behaviors. So we want to complement other mechanisms, be able to dynamically adapt to potential exploitations and threats. There needs to be an element of self-awareness, contextualization of the environment, and retention of that knowledge. And how do we improve the utility and detection capabilities? And lastly, how do we analyze the data in an efficient manner? These are all grouped into 5 different subsystems that we'll go into a little bit of detail. Each one of those subsystems perform a complementary role within the bigger model itself. So we're going to change the characteristics of the subsystems. There's 5 main subsystems in the model, which we'll go into just now. Each one of those can have one or multiple different types of agents. And inside each of the subsystems, there might be 1,000, 1,000,000 different kinds of agents, instances of those agents as well. So these subsystems can, for the most part, independently exist inside this model. There's no need for all of them to be present at any given time. There might also be a case where some of the subsystems might exist on certain sub-networks and others on other networks, so there's the ability for these agents to communicate and migrate across. High-level view of the model architecture. In a nutshell, we've spoken about this continual self-evaluator. That was part of the title of the model, the CESIMAS model. And I want you guys to focus on, maybe a little bit less about the details, just you'll see there's a controlled direct loop. What that basically means is every single thing that happens in this model is being measured, being monitored, there's an action that happens, there's some outcome of that action, and the model learns about it. So it's a continual direct control loop, where we try and retain knowledge. I took this action, was this action good? Yay or nay? And then incorporate the feedback back into the model itself and potential future agents. Okay, so hypothetically we've got our critical infrastructure environment. On top of that we'll go into each one of these in a moment. We've got a data collection component, an analysis component, a was this right or wrong kind of like mediator component, and then we've got at the top our self-awareness. And self-awareness, how do we learn and improve future decision-making processes? So a whole lot of text, and I'm going to try and summarize this for you guys while everyone reads off the slide. Effectively, the RECONNAISSANCE subsystem is responsible for collecting data in near real time. Each one of the agents in the subsystem has a relatively small subset or kind of like a know-how of what the environment should be, that notion of the self. The purpose of them is to apply a heuristic function in a dynamic way to determine is this potential data point that I've collected anomalous or not. It's not saying it is, it just says is it potentially anomalous. Once it's potentially flagged, this thing can either be a false positive or can be a true positive. It passes on to the detection subsystem, once again a collection of different agents. The detection subsystem is installed with a set of knowledge. These agents go through this and also apply their own heuristic function to determine is this truly anomalous or not, and to what extent. Now I think the important thing to note here at this moment is that what is considered anomalous is going to be dependent on the organization. Each organization will have a specific level of what it would tolerate within its system, and same for the immune system. I might get infected by the flu and become sick quite easily, but the next person might not. We've got the responsive subsystem. So once this piece of data point has been analyzed and now determines, well, this is a malicious thing, it gets passed on to the next agent, where these are kind of like the doers. They say, hey, here's this potential malicious element, we know how to solve it, go and attack that element and kind of like engulf it. Similar to how an antibiotic would act against a foreign element or the flu. Lastly, we've got we've got the self-awareness and knowledge retention. So once this agent has now gone through this whole process and has removed this foreign or this malicious element, it says, well, my action had some outcome. I need to learn from this, contextualize my environment, and say, well, was this an ideal utility or an ideal state or not? That information is then captured and communicated to the next subsystem, next set of agents, where they deliberate through this and determine what the level of utility was. That utility is then feed back into a knowledge repository, maybe it's the equivalent of a database, and that database is then used to train future agents. So this whole direct control loop cycle. The purpose of this process is to, at the end, similar to how your body would discard cells, future cells might be trained on more updated data sets, potentially improving the utility over time. That's the idea behind it. We've also got 2 different types of the components. We had a facilitator subsystem that's purely to prevent, or to the first part, I remember if you guys remember there was a facilitator subsystem and a mediator. Facilitator is purely there to ensure that communication can occur. And the mediator introduces a little bit of redundancy, but that's purely to implement it on the fact that we don't want certain elements to suppress others. All of those agents are grouped into 3 different aspects. The first one is the omni-awareness aspect. We've got reconnaissance, detection, and response. We've got the well-being aspect that focuses also a little bit on response, self-awareness and knowledge, and then the user interaction feedback, driving mediation, facilitation, and that direct control cycle. So a prototype was implemented using graph theory, and a little bit of a GUI was developed. The whole purpose of this little graph theory was just to illustrate computational resources, agents, and then obviously foreign elements in this environment. There's a bit of an agent training process, so similar to how cells would be produced, and these cells are naive, they don't know anything. Those cells then get passed through this long process until the cell becomes a B cell or a T cell, or takes on some specific format in the immune system. And so the result was quite interesting. So if we had to implement this in an environment, which I'll show you some of the results just now that we've done, we would want to have this implemented in a way that doesn't necessarily consume additional resources, financial or computational, but also improve the level of security within an organization depending on the appetite of the organization. A lot of data points. I want you guys to focus on these little black bars are effectively, there's a little bit of a scale missing. Let's say it's a scale of 1,000. If we introduce one foreign element, you've got one little strain of a flu antigen that comes into your body, you might get sick. A small little amount of potentially malicious elements can have a large impact on agents that get infected, cells that get infected and you become sick. So a small little foreign malicious attack can have a massive impact. And over time, this red line introduces the utility states of the environment, where 100% being perfectly, what's the English word for gesond now?
Healthy.
Healthy, perfectly healthy. Thank you. So over time, as we've got this direct control cycle, you can see the level of utility starts off not so great, but you go through this training process, and over time, the level of utility climbs up to, and I think the final result was about almost close to 90, 89 point something %. Once again, it's going to be dependent on the organization's appetite. The organization might be very strict right here, which means your level of utility might take a couple of iterations to get to a suitable point. Interesting result, and I think this is the second last slide, was when you define anything that contains a self set, there's going to be a level of diversification inside the set. And a common problem with anything that utilizes a self set is stagnation. Stagnation being we've got lots of the same things, and there isn't really like any difference between the different things. And so what was quite interesting though, that populations of agents in these different subsystems across networks, they started off with a lower level of utility, actually grew up at the end to have a high level of utility as opposed to guys started off higher. Purely because there's a mutation operates inside the agent generation process as well. Thank you. Any questions?
We've got time for one.
Sorry, I know it's a lot to take in. Yes?
Okay. I've got two, but they can be short. One, okay. It sounds, you didn't actually mention explicitly which artificial immune algorithm you're using. It sounds like negative selection.
It's a combination, positive selection, negative selection, danger theory.
Oh, okay. So
that forms a core part of it. There is a cryptographic element of it during the agent generation process, where we utilize a cryptographic kind of like seeding process with a little bit of a mutation operator to prevent stagnation from occurring.
Can I squeeze them on more?
Yeah,
Okay.
but Prof. Orloff also wants to ask.
Yeah, but it's just a small clarification. The word, using the two words evaluation and self-awareness, what does it mean in this particular context?
Sorry, just say self-awareness and?
Sorry?
Self-awareness
so,
and?
for instance, yeah, because for instance the title was the evaluative self-aware system, right? So self-aware obviously can be defined completely differently. For us, it is just a information structure,
yeah.
And actually the only difference if it is supposed to be static or dynamic. So this is what inspires my question, that what is your particular interpretation
Self-awareness
of
is
awareness, and how large this information structure is what you assume to be necessary for a reasonable level of self-awareness.
So self-awareness in this context is purely subjective around the organization that's being implemented in. So we kind of abstract this concept of an agent. An agent can have some self-knowledge of the environment that operates in, but we want to try and give this agent the ability to learn. We can tell, well, Jan, yes, Jan is an agent. Jan, this is how this environment works, but moving forward, I want you to learn. We kind of give you a basic knowledge of the environment, but over time, you need to build up your own understanding. And that's where my top level of my model came in, the self-awareness component. You need to grant, every agent will need, we had a conversation yesterday around how subjective or objective are agents and general decision making inside of physical systems. And the argument was kind of like, well, can you truly be objective if a person is always subjective? And so we're saying, well, yes, there's some subjective self-awareness, and we're saying, well, within this organization, this is how data collection and security works, and then just over time, create your own kind of like self-awareness. Learn the environment and apply things to it.
But you see, this is the sexy part of your work, that you are talking about organization, and actually the scoping of the awareness is a big problem. I mean, the higher scope, what is the scope of that sort of domain where you have to build awareness, and how homogeneous, how balance this?
Exactly. So
10 papers on the...
Exactly. I know we're cutting time short. So part of the research goes into my PhD model that I'm working on at the moment. And the interesting part is, how many agents should you have? Should I have 1 million sitting on the species? And those million have little, like let's say 1 million of knowledge or self-awareness? Or should I have 1 or 2 or 3 that has a little bit more knowledge? But then if one of those become infected, what's the impact going to be on the rest? And it's kind of that final little process where you need to work out. And that might differ from company to company, organization to organization as well.
Okay, I will allow Duncan's question, otherwise he's going to have a...
I actually think I can see the communication breakdown, and it doesn't matter. Because I think when you say self-awareness, because I had a very similar question for my question to Professor, but I think when you say self-awareness, you're looking at it from the point of view of the organization, awareness of the self in that sense, not from an individual agent.
Not from an individual point of view.
Awareness of the structure of the agent. And then you wouldn't even have to change your acronym, you could just call it situational awareness, and then it stays exactly the same.
Oh, maybe you must consider that.
And the reflexive awareness. The self-awareness means that it is reflexive also, not only self.
Well, that's the situational awareness might be better then.
Exactly.
Perfect. Thank you guys.
Very good work.
Thank you.